All right, discrete math. It's time for us to start a new subject. So this chapter 2 is going to be about sets, and then later in the chapter we're going to get into functions, which are really sets. But I'll explain all that later. So one of the reasons we're studying sets is because sets, the theory of sets, which we can call set theory, is a foundational theory in mathematics, upon which basically all of math is based. So everything really starts with sets. A set is one of the simplest ideas in mathematics. It is just an unordered collection of elements. So you have a bunch of things, you put them together, and they form a set. That's it. And it's also one of the fundamental objects that computer programmers work with as well. So first of all, let's go over some notation. We have this symbol, which I've already used, I've introduced and talked about it. It's this symbol, which means is an element of. So when you have a thing, which is part of this unordered collection, it's called an element, and the collection itself is called the set. So we could write, for example, little a is an element of capital A. It's not uncommon to use capital letters for the name of a set and a lowercase letter for the element of the set. However, that is by no means a rule. For one thing, sets themselves can be elements of other sets. That is allowed. So just be prepared to see that happening occasionally. What if we want to say something is not an element? Well, let's pretend B is not an element of the set A. You can just put a slash through this symbol like that, and that means that it is not an element. So let's talk about different ways of representing sets. The first way, and probably the most basic way of representing a set, is what's called the roster notation. So I could say that the set A is equal to, and then I use curly braces. These symbols here are called braces. Some people call them curly brackets. I'll be calling them braces. That is sort of the technical name for them. And then what you put inside here is just a set of things. So let's say this is a set of numbers, maybe 1, 2, 3. There we go. And then I close that off. So that's a set. It's got 3 things in it. Obviously, this notation is not very convenient if the set has an infinite number of things in it. However, sometimes you'll see a ... that represents that some pattern that's been established continues. Now, one point I want to make about this set is exactly the same set if I write the elements in a different order. It really doesn't matter what order the elements are written in because the set itself is just the collection of things. The set itself is unordered, so the order in which I write them doesn't matter. It is never, you never see elements repeated, so 1, 1, 2, 3. You just never see an element repeated like that because it doesn't really have any meaning to write an element more than once. Once you have said that the element is in the set, you don't need to say again that the element is in the set. It either is or it isn't. You can't have 2 copies of the same element in a set. So that is something you just wouldn't see. Okay, so that's roster notation, one way to do it. Another way to talk about or write down a set is this thing called set builder notation, which is also called truth sets. And the set builder notation is essentially saying, let's define a set. This time I'm going to call it S. Let's define it by saying it's the set of all things X, you introduce a variable, that are elements of some domain. That domain might be implied, or it might be stated explicitly right here in the notation. And then you use this vertical line, or sometimes a colon in place of that vertical line. And that just basically is shorthand for such that. And you follow that up with some predicate about X. So this basically means it's the set of all elements X in this domain such that this predicate is satisfied. So you say some statement here. Here's an example. The set A that I defined up here, 1, 2, 3, this could be written down as the set of all X that are elements of the set of integers, 1, 2, 3, and 1, 2, and 3 are all integers, such that, and then maybe they satisfy some inequality, like 0 is less than X is less than 4. Well, yes, the only integers between 0 and 4 are 1, 2, and 3. So that would be the set of all things that satisfy that inequality. Now, you got to understand that what this is saying is that anything in this domain that satisfies this inequality is in this set. and only the things that satisfy this inequality are in this set. So when you write a truth set, it's exactly the set of things in the domain that satisfy the condition. Or conditions. You can have more than one thing over here by just conjoining statements together. One other example that I want to mention of this, I forgot. This is the set 1, 2, 3. Just wanted to point out that's the same thing. Another example I wanted to mention is here. I'm just kind of showing you what this can look like. What if I want the set of all points x comma y, which are elements of R2? This denotes the like the xy plane. Okay, so this is like two-dimensional real space such that x squared plus y squared equals 1. Well, that would be a set of points in a plane. So the points in the plane, xy, and x squared plus y squared equals 1, this is an equation. It's saying if x and y satisfy this equation, then it's in this point. Well, this right here is the unit circle. So the unit circle itself is a set of points of this format that satisfy this equation. So you could write the unit circle like this. So there's just a couple of examples. Now I want to go over these common sets of numbers. I've used a lot of these before, like integers and rational numbers we used at the end of chapter 1. Real numbers you probably are aware of, but I just want to go over all of these, especially this definition of natural numbers. The natural numbers for the purposes of this class are defined to include 0 and then all the positive integers. So 0 is a natural number. Not all textbooks use that definition of natural, but this one does, and I do. Integers, of course, include negative integers, 0, as well as positive integers, like that. Positive integers, this is denoted by z with a little superscript plus. That starts at 1. So the positive integers and the natural numbers are different in that natural numbers include 0, positive integers do not. You can also, by the way, talk about the negative integers, which would be z with a little negative sign up there. The rational numbers can be written in set builder notation by writing the set of all a over b such that a and b are both elements of the integers, and of course b is not 0, because you don't want to have 0 in your denominator. So anything that can be written as a fraction of integers with a non-zero denominator is in the set of rational numbers, and it is exactly the set of all those things. So that's an example of using set builder notation. Now the real numbers are kind of hard to write down. I'm just going to draw a line and say this. It's the continuum. Actually defining the real numbers is quite hard to do, and it involves something called, well, there's more than one way to do it, but the way I learned to do it involves something called Dedekind cuts. And I'll probably mention Dedekind again a little later in a future video. So we'll get back to that. And then finally, the set of complex numbers. This is, of course, the set of all things that look like a plus bi, where a and b are elements of the real numbers, okay? And of course, I is defined by saying I squared equals -1. So that is the definition of your imaginary unit, right? It's the principal root of the number -1. So that's an introduction to sets. Next, we're going to go over a bunch of definitions.